Hello, this is video number 24 entitled Free Body Diagrams and More Forces. I'm going to start talking about more forces. We've already talked about weight, but we need to know about a lot more in order to be able to do Newton's second law problems. So the first thing is a free body diagram. So I have here, it's used to illustrate all the external forces acting on an object. So I have a few examples. On the left here, there's a picture that shows a book on a table, and it shows four different forces. FTB, the force of the table on the book because they're in contact. FBT, the force of the book acting on the table, again because they're in contact. And these two forces here are action-reaction forces. You see the subscripts are switched and they're just in opposite direction. The table pushes on the book pushes on the table. Likewise, we have the force from the earth on the book, which we also call the weight of the object. And that means that if the earth is pulling on the book, then the book is also pulling upward on the earth. So out of these four forces that are shown here, we're only going to want to include two of them in the free body diagram of the book. And they have been shown here on the right. The force of the table on the book and the force due to the earth, the force of gravity. We only want these forces on the free body diagram because these are the forces acting on the book. The other forces here, this one was acting on the table, this one was acting on the earth, so we don't care about them because we're drawing a diagram to represent all the forces acting on the book. In the other picture here on the right, we have a force 1 and a force 2, two different people that are pushing on this person. And then there's also a picture that shows that the total force due to F1 and F2 would be to the right and upward. But the free body diagram for this person here with the blue shirt would only have F1 and F2 because those are the forces acting on that person. The total force, the net force, is just a result of the two forces. It's not a separate force. It would not be included in the diagram. So I have a few steps on how we draw a free body diagram. We're going to choose a convenient coordinate system. For now, this is the simple Cartesian coordinate system xy, where x is horizontal and y vertical. Later, we might have to rotate this coordinate system. We'll get to that soon enough. Second step is to draw the object as a point or a box. Technically, you're supposed to draw it as a point, but I usually prefer to draw it as a box just because it's easier to show all the forces acting on the object, in my opinion. And then step number 3, indicate the forces acting on the object with the arrows extending outward from the dots or the points. So this is what we saw in the previous slide. We were only drawing the forces acting on that one particular object, and the forces were always originating from the object. If we go backward here, you see that originally the forces were pointing toward the object, but we moved them in the free body diagram here so that they were pointing outward from the object. This just makes it easier to see all the forces that are acting on this object. Because if they start pointing toward the object, then maybe you're going to think that those forces are acting on a different object. And finally, step number 4 says we have to label each force. So in order to be able to draw more free body diagrams, which will help us solve Newton's second law problems, we need to talk about a few more forces. The first one is a tension force. I've defined this one as a force along the length of a medium such as a string or rope. So if there's a rope or something that's attached to an object, then there's going to be a tension in that rope. The direction of this force is always in the direction of the string away from the object. So if you're looking at the mass here, then the tension in the rope would be away from the object. But if you look at the hand, you can also think as if the mass is pulling down on the hand. So there is a tension away from the hand as well. But if we're going to draw a free body diagram for the mass here, which we have done here, then we don't care about the tension acting on the hand. We only care about the forces acting on that one object. So there would be the tension going upward and a weight going downward. Tension is a force, so the unit is a Newton, and it's a vector. I have a little saying that I usually have my students say it out loud together so they don't forget. One string, one tension. All I mean by this is that, as you can see in this picture, you have one string here. So that means that this tension, the force pulling down on the hand, must be equal to this tension, the force pulling up on the mass, because this tension is along the same string, so it must be the same tension. Let's talk about one more force, the normal force, which is the force exerted by a surface against an object that is pressing against a surface. You can see in this picture here there's a bag of dog food, and we have its weight going down, but we also have the normal force, which we use the letter N. And this normal force is due to the table pushing up on this bag of dog food. If we go back to a couple slides here, we had the force of the table on the book here. Well, we could actually call this the normal force, because it's the surface pushing up on that book because that book is pushing down on the table. So the normal force happens as a reaction to an object pressing on the surface. That surface is going to press back on the object, and that force is always going to be perpendicular to the surface. So that's how you know in which direction to draw that normal force. So force, so it also has units of newtons, and it's a vector. I do have a note here that the normal force is not always equal to the weight of the object, and we'll see this soon enough, but from the free body diagram here of the bag of dog food, you might think, oh well, there's a normal force upward, there's a weight going down, the bag of dog food is in equilibrium, it's not moving, so they just equal each other. And that is sometimes the case, but not always. So we'll take a look very soon on how do we know exactly what the normal force is equal to. The last thing here I have a your turn and then an example. So this your turn here, we have the ball hanging from the ceiling by a string is pulled back and released, which is the correct free body diagram just after its release. So we're just getting practice drawing free body diagrams. We've learned about weight, tension, and normal force. So let's see if any of these forces apply in this picture. Whenever there's an object, there's always a weight going straight down. So choice D is not good because there's nothing going straight down. Whenever there's a string, there's a tension pointing along the direction of the string away from the object. So we're looking at the free body diagram for the ball here. So the tension has to point away. So this one's not good, A here, because it doesn't have a tension. So we're left between B and C. Well, there are no other forces, there's just tension and weight. You may think, oh, well, the ball is moving this way, so maybe there's a force this way. But if you can't think of what is causing that force, it's probably not there. So there is no force pulling it this way. The reason that the ball is actually moving that way is because that tension force pulls it to the right, and the weight pulls it downward. So it does move in that direction, but there's no extra force. So the correct answer is B. And the last thing I have here is example 4, and we're just doing 3 more free body diagrams to get some good practice in. So we have the object on a surface, draw the free body diagram for each case. So I'll draw it as a dot, the book or the object, and draw all the forces. So we've already seen this one. There's a weight, and we have to label it, and there's a normal force because there's a surface pressing upward on this object. And for all of these, we're going to use a standard coordinate system, x and y. X is horizontal, y is vertical. For the second diagram here, it's very similar. We still have the weights. And actually, this is a reason why I like to use a box for the object, just because we have the weight that is pulling down on the object, but there's also an applied force this hand is pushing down. So that's going to be another downward force. So I just like to have a box so I can put the forces next to each other. And I'll call it FH, the force from the hand. You could also call it FA for the applied force, whatever that you want. And there's a surface, so there's a normal force pointing away from the surface and perpendicular to the surface. And the last one here, we'll draw the object as a box. We can always draw the weight going straight down. If there's a surface force, there's a normal force pointing perpendicular away from the surface. And then this time, there's a hand pushing at an angle here. Since we always like to draw the force coming out, pointing outward from the object, the force is going this way to the left and upward, but I'll have it originating from the object, just so I see all the forces coming from the same location, all acting on this object. And I'll call this FH. And those are all the forces that we know about. We're going to do a lot more practice with free body diagrams and using them to solve Newton's second law problems coming up soon. Just to recap, the weight is always straight down in a free body diagram. Tension is always away from the object, and the normal force is always away from the surface and perpendicular to that surface.